Right. Hello, everybody. If I sound a little bit different, it's because I am recording this at home because somebody was working in my office. I mean, my podcast studio was under construction. That's what I mean. Anyway, we're going to talk about another sequential data structure here called stacks, like that. So stacks can be built on top of vectors or arrays or singly linked lists. You could build them on top of doubly linked lists, but there really isn't like a reason to. It doesn't really add anything to it there. And they're not more powerful than like lists or arrays. They're less powerful. Like they restrict you to a smaller set of operations. All you can do with a stack is you can add an element, and you don't say where it gets added. That's chosen automatically. You can remove an element, and again, you don't say which element to remove. And you can check to see if the whole thing is empty. Stacks, what you can use them for is sort of like a to-do list kind of thing, tracking like tasks that you need to perform. So you add a task to the list when you discover that you need to do something, and then you pull a task off to sort of do it and then remove it like that. That might seem like a kind of like a limited application, but it turns out that lots of problems can be phrased in terms of, okay, I have a bunch of tasks and I want to keep track of what do I need to do next there. So a stack, we usually sort of draw it vertically as this kind of like stack, like a pile of things here like that. And only the top value, only the thing on the top of the stack is directly accessible. So our key operations are we can push new values and they go on the top of the stack here. So the top is the only part of the stack that we have access to. We can pop values off, and that removes the top value from the stack. Again, the top is the only thing we have access to. And then finally, we can ask, is the stack empty or not there? So that's just true if it's empty and false if it's not. And the reason why empty is important is because it's illegal to pop from an empty stack. So we need a way of, before we do a pop, asking if the stack is empty or not. All right, so let's just trace through a few operations on a stack here to get a feeling for what does what here. So we'll start with an initially empty stack. Usually, like when you create a stack, it starts out as empty. So empty is true. There's nothing on the stack here. So if we do a few pushes, for example, if we push 1 goes onto the stack. It becomes the top. And of course, empty is false now because the stack isn't empty anymore. Then we push a new element, 2. That goes on top of the 1. So 2 is the new top and 1 is below it. And then if we push 3, that goes on top of the 2 and the 1. Now, if we start popping things off, we'll see that the first thing to come off, of course, is the 3. And then if we do another pop, the 2 comes off. And then if we do another pop, the 1 comes off and the stack is empty here. So the important thing to notice is that things come out of the stack in the reverse of the order that we put them in here. So we put them in the order 1, 2, 3, and then they come out in the order 3, and then 2, and then 1. Sometimes stacks are called LIFOs, L-I-F-O, which is short for last in, first out. So the last thing to go in was 3, and it is the first thing to come out when we start doing pops there like that. So stacks are LIFOs, last in, first out structures. Now, besides push, pop, and empty, there's sometimes a few other operations that are like convenient to have. So we have to have push, pop, and empty. If we don't have those, we just don't have a stack here. But there's these other operations that it's sometimes convenient for them to be available, but they're not like essential here. So like it's nice to have a way to look at the value on top of the stack without removing it. Sometimes that operation is called a peek. Sometimes it's called a top there. So whatever it is called, it returns the top value, but it doesn't remove it there. If we build a stack on an array, then we may choose to sort of have a fixed maximum capacity, like the bag class that we sort of did earlier there. So if that's the case, we need a way to check and see if the stack is full, because it's illegal to push onto a full stack there. And then finally, it's nice to have a way to just ask, like, how many things are on the stack? What's the size of the stack? Like, if you didn't have a way to, like, get the size of the stack, you could just do that yourself, right? You could just add an int variable and increment it every time you push and decrement it every time you pop there. So it's not like, if you were missing one of these, your life would be over. But they're convenient to have under certain circumstances. There's two sort of error conditions that can occur with stacks. You can have a stack underflow, which is defined if you try to basically access the top. So like if you try to pop it off or look at it, either of those require us to like access the top element, right? And the stack is empty. So if the stack is empty, there is no top element, so it's illegal to try and remove it or look at it or return it or something like that. So that's called a stack underflow. And that can happen in any stack because any stack can become empty. But if you have an array-based stack with a fixed maximum capacity, then you have the possibility that the stack can become full, and it's illegal to push onto a full stack. So we call that a stack overflow. Not every stack will like suffer from stack overflow if you don't have a fixed maximum capacity, either because you're building it on like a vector or you're building it on like a linked list, then stack overflow just doesn't apply to you. Depending on like what you're doing, right? Like stack underflow and stack overflow, those might be like actual exceptions that you're throwing, or maybe you just print an error message, or maybe you just do nothing. Like maybe if you try to push onto a full stack, just like nothing happens. So, but those are like error conditions, right? You have to sort of decide like what do you want your stack data structure to do when these things happen. You can build a stack, like we said, on top of a singly linked list or an array or a vector. The important thing is, however we choose to build it, we want all the key operations. So push, pop, and empty, right? Those are our key operations. Push, pop, and empty. Those need to run in O of 1 time. Ideally, all the other operations too, but definitely the sort of key ones need to run in O 1 time. They're like that. If we build a stack on an array, we can use like a fixed maximum capacity, or we can treat it like a vector and like double the capacity when we sort of need to there like that. That would also work. So push and pop, they're going to add remove elements from the same end of the sequence here. So if we're building it on a linked list, we sort of have two choices about how we can build it. We can do pushes and pops both at the head, or we can do pushes and pops both at the tail. We can't do a push at the head and a pop at the tail. If you do that, you have something else. You have something that's not a stack there. A stack, like both of the add and removes, operate at the same like end of the sequence there. But we can sort of choose which of these two things we want to do. But it will turn out that there's like a strong preference for one particular way of doing it. So if we do push and pop at the head, that means the stack push basically translates into a push front. And push front is O of 1. So that's good. That's what we're looking for, right? Then pop, right, the stack operation pop, translates into a pop front, which is also O of 1. So both of those are sort of good. We're good to go there like that, right? Since we're only using the front of the list, we only need a head pointer. We don't need a tail pointer. That's kind of nice. Like it's nice that we don't need an extra pointer in our class to sort of keep track of where the tail is like that. But the crucial thing is both of these are O of 1. So that satisfies our requirements that both push and pop be O of 1. If we do them at the tail though, so then the stack push becomes a push back. And that's O of 1, but it requires us to have a tail pointer. Like we need to have like a TL pointer inside of our class there like that. So we need an extra pointer in our class. Well, that's not such a big deal there, but it is something that like the push and pop at the head doesn't require there like that. But the main problem is pop is going to become pop back. And on a singly linked list, pop back is O of n there. Now we could fix that, right? We could make this O of 1 if we went to a doubly linked list. But now we have not just an extra tail pointer, now we have an extra pointer in every single node. just to be able to do pop back in constant time there like that. So that's really kind of like overkill for our purposes here. So we need both a head and tail pointer, and we have this O of n on pop back over here like that. So that kind of rules out doing push and pop at the tail there like that. If you did push and pop at the tail, right, you would still have a stack, but you would have a stack that is like sort of slower than what you expect, right? You expect push and pop to be constant time. You don't expect pop to randomly take like O of n time like that. So if you're going to build a stack on top of a linked list, there's a very sort of strong preference for building it where we only access the head there. That simplifies the implementation because we only need the head pointer, and it satisfies our requirements on the runtime of those two operations. Now, if we sort of think about it here, right, so like push, that's going to become push front, like that right there, right? And pop is going to become pop front. And for our list, right, push front and pop front are both just special cases of insert. So our insert has 4 sort of separate cases. Pop is, implementation of erase. Pop front is a part of erase here like that. I misspoke, right? And push front comes from insert, right? So both of those have 4 cases depending on where you're doing the insert, where you're doing the erase here. But we're only ever operating at the head, and we don't need to store a pointer to the tail. So cases 2 and 3 were all about updating the tail pointer. So that means we don't need to pay attention to those. Those are just gone. Like they sort of they don't apply here because we don't have a TL pointer to update. And then because we're only operating at the head, not the middle of the list, that eliminates case 0. Case 0 was all about inserting between 2 existing nodes or deleting a node that's between 2 existing nodes here. So of insert and erase, only case 1 is the one that we need to worry about there. So our insert and our erase code isn't going to have that 4-way if-else kind of code in it here because there's only one case to think about. So this is our skeleton of our linked list based class here for our stack here like that. So under the hood, right, the private data section, everything looks kind of familiar. We have the same sort of node structure that we had before with a value and a next pointer. We have a head pointer. We have no tail pointer because we don't need it. And then we have a variable to track the size. And the reason why we have that is because we want to make the size function run in constant time there. If I didn't have the int sz, then the size function would have to loop through the list to count all the nodes, and it would need to run an O of n time there like that. So that's the only reason why the int sz is there. If we didn't have the size function, right, then I wouldn't need the int sz part of it there like that. But we'll have them all in here just to sort of see what they all look like that. And then up here, of course, we have our required operations, the stuff that is sort of mandatory for us to have a stack there like that. So empty, top, full, and size, those are all pretty simple to implement, right? So when is our stack is empty? Stack is empty when the list is empty. What does an empty list look like? It is a list where the head is a null pointer, like that. So we just check to see if the head is null pointer. Now, since we have that sz variable, instead of checking to see if the head is null pointer, you could also just say is sz equal to 0, and that would also work. But head is null pointer is the general one. We don't always have that sz in all implementations of stacks there. Similarly, a linked list based stack can never become full. We can always create more nodes, at least until we run completely out of memory, and then it's somebody else's problem. So this is even easier. We just always return false. We're never full. If you ask for the top, this is the first place where we need to worry about stack underflow here. If the stack is empty, then you can't ask for the top. There is no top. So this is where a stack underflow would happen. This here, this sort of place where it just says stack underflow like that, That's just a placeholder for whatever it is you want to do when a Stack Underflow occurs. So that might be like throwing an exception or printing an error message or whatever there. Like replace that with whatever it is you actually want to do. But if the stack is not empty, then we just return the value inside of the head node. That's always the top. The head of the list is the top of the stack. And then, of course, if you want the size, that's why we have the SZ variable. We just return whatever is in the value of SZ. So long as we're remembering to increment SZ in push and decrement it in a pop. So all of those are nicely O of 1. For push, again, this is basically insert, but only case 1. So we're only worried about that sort of case 1 of an insert here like this. So if you want to, you could go back to the linked list, the singly linked list, sort of insert notes and sort of follow along and see how this follows with what case 1 says to do here like this. So we're starting out with our head pointer pointing at some, like this is the sort of current head, this is the top of the stack right now, and we're wanting to push a new value in front of that there. So our first step is to create the new node n. So n sort of is summoned into existence by the allocator finding memory for it there like that. Then we set n's next to point to the old head, the previous head there like that. And then finally we update the head to point to n. So now n is the new top of the stack there like that. Now one thing to notice is these also work for the very first push when the list is empty. So like imagine that the head is null pointer. Right? So step 1, just to sketch it out here, we create a new node called n, right? Step number 2, we set n's next to null pointer, set n's next to what the old head was, but that's a null pointer there like that. And then the final step is we're going to update the head to point to n. Right? So these 3 same steps work for the very first push and then for all pushes after that. I don't need a special case for like the first push that creates the first node there like that. In the linked list, we needed a special case for creating the first node because we had a tail pointer, so we had to make sure that the tail pointer got updated in that case. No tail pointer means that's not a special case, which means these 3 steps are all we need to create new nodes to sort of push things to the front of the list, regardless of whether the list is empty or has like a million things already in it there. So the implementation of push is pretty short here like this. This is step 1 right here. That's step number 1. This is step 2 right here, like that. And then this is step number 3 down there. And then, of course, since we have the size, we need to update that. Again, if we didn't have int sz as part of our class, you wouldn't need to sort of increment it there like that. Now, it turns out that you can actually compress this down to just exactly 2 lines of code. So remember what our node structure looks like. It looks like this. It's struct node, right? And then it has an int for the value first, right? And then a node pointer for the next part of it there like that. That's what our node structure looks like. So when you create a node, you can do it like we do it up here where we just say new node and then we fill in the value and the next like sort of one by one. You can do that, but you can also fill in everything all at once. And that's what we're doing over here. So we're creating a new node, but then inside the curly braces, the first value in here, that is going to become the value of the new node. And then the second part in the curly brace, that's going to become the next of the new node. It just follows the order that is given in the original like node structure declaration. So the first thing and the second thing in the curly braces become the first thing and the second thing in the sort of node there like that. So that creates my new node and sets its value and its next all in one go. And then I don't actually even need n, because what do I do with n? Oops, I misspelled it down here. That should say n like that, right? All I do is put it into the head there like that. So we can just do that directly. Just take that new node and say that becomes the head there like that. and then we increment the size. There's no like runtime difference between the two. It's not like one is faster than the other or anything like that, right? It's just a matter of like, fewer lines of code there. You can argue about which one is more, idiomatic or easier to understand or whatever, but I just wanted to sort of show you that you can do that. Now, pop is a little bit more code just because we have to deal with stack underflow. So that means we need an if at the beginning of check and see if it's empty. And also because we want to return the value that we're popping off. Not all versions of pop do that. They don't all like return the popped value. Some of them return void, but our version is going to return the int that we're popping off here. So the first thing we have to do is check for stack underflow. So if the head is null pointer, that means the list is empty. So then we just abort with a stack underflow error. Again, whatever you want to do for that, like throw an exception or whatever, like this is where you would sort of do that there. So if we get beyond step 1, that means the list is not empty. That means we have at least one node here. In this picture, I've shown it with 2 nodes, but it would also be the case where maybe I only have one node, right? And that node is the head, which means that is the top of the stack there like that. So what we're going to do is we're going to set another pointer called n to point to the head there like that. And we're doing that because we're going to move the head pointer. So I need something to sort of save the pointer to the node that I want to erase here so that after the head moves, I still have access to it there. Then I'm going to move the head, so the head points to this one. So now this is the new top of the stack there like that. And then we can delete the end node there like that. Now we have to do a little bit of extra work here because we want to pull the value part out of the end node before we delete it. So that'll be just like an extra int variable, but then that's nothing about that right there. And the other thing to notice is these also work when n is the last node. So if we sort of sketch it over here, right? So let's say that that's our head, right? Like that. So we make n point to that, right? Then we're going to set the head to point to n's next, but n's next is null pointer. All right? So that means that my head is going to become null pointer like that. And then we delete n, but the head is now null pointer, so that means my list is empty there like that. So it correctly deletes the last node. Again, like I don't need a special case for deleting the last node because I don't have a tail pointer to update. The same steps that work for deleting, the 30-second node also work for deleting the last node there like that. So no special case here. So in code that looks like this, right? So we've got our check for stack underflow up there like that. And then we get down here. So this up here this is step number 1. This is step number 2. Here we're saving the value inside of n into a local variable x because we're going to delete n and we can't get its value after it's been deleted. Then this here is step number 3. And then this is step number 4. Okay, right there. And then we decrement size and we return the value that we pulled out of the node down there at the end. There isn't really like a way to simplify, pop down to like a one-liner or anything like that. So that's just what it looks like there. Now, in our version, like we return the value that we're popping off, which is kind of convenient here, but not all stacks do that here. Like if you just do hashtag include stack, the C standard library stack pop returns void. So in that case, you need the peek function to sort of get access to it there. So you have to basically look at what the top of the stack is before you pop it off. So this is the sort of pattern if you're using the standard library stack. You have to look at what the top value is with this top function and then pop it off. It's kind of like a 1-2 kind of thing there. It's a little bit inconvenient because a lot of times we want to pop a value off and like look at it at the same time. But that's just how they chose to sort of implement it there. So just be aware of that if you're using the standard library stack. It doesn't work quite the way that like our stack class sort of works here. Now, if we want to build a stack on an array, it works kind of the same as like a bag or the ordered array or something like that. The array behind the scenes is bigger than we need it to be, and we just keep track of like how much of it we're sort of currently using here. So under the hood, we have our array. We have cap, which is the size of that array. It's like the capacity of the ST array there, like that. And then finally, we keep track of like how much of it we're using with T, which is the index of the top of the stack. So when the stack is empty, T is -1. That's what sort of -1 means. It means that the stack is empty. Add a little comment over here, right? That's what an empty stack looks like, is T is -1. So again, like empty, top, size, full, those are all easy peasy, right? We can do size is just going to be T plus 1. So if the stack is empty when T is -1, then if you just add 1 to T, you get the current size of the stack there, like that. And then empty is just based on this size function over here. So this size there is just calling that size function over there. When's the stack empty? When the size is 0. When is the stack full? When the size, which again is just this function up here, is equal to the capacity. And then the top, well, again, we got to check for stack underflow first here. So as long as we're not empty, what is the top? The top is just whatever is in the array at the top index there, like that. So sort of easy like that right there. And note that all of these are like O of 1, right? There's no loops or anything sort of going on in any of those there. So they're just pretty straightforward. Right? So to figure out how push and pop are going to work here, let's look at like an empty stack with capacity 8, and we'll push a few things here. So this is a freshly created stack. It has a capacity of 8, but it's empty, so that means T is -1. There's nothing on the stack here. So let's push a few things and just kind of think about, like, you know, where should they go in the array? So like if I push a 1, right, you could put it anywhere in the array, but we want it somewhere where we can like sort of keep track of it. So we'll put it at index 0, and now T is 0. So T is the index of the top of the stack, right? Where's the top of the stack? It's at index 0. If we push another value, that goes in sort of like the next available spot. So index 1 is after index 0. So we just increment T and then put the new value there. So we can kind of get a feeling for like how this works, right? As we push, we add things going in this direction by incrementing T to kind of move it in that direction there, like that. When T gets all the way out here, that's when we're full there, like that. So the implementation of push is, so first of all, we got to check for stack overflow. If we're full, that means we don't have any more room to add any new stuff there, like that. Otherwise, we just increment T and then place X in the new sort of location where T is in the array there. And if you're familiar with like the pre and post increments, you could do a one-liner of that as just ST plus T equals X, right? The pre-increment, doing the increment here before the T there, like that, means that the increment happens before sort of everything else in the statement there, like that. Generally speaking, it's like, considered a little bit more sort of confusing to rely too much on like pre and post increments. So I'm not going to do that, right? But if you wanted to make a one-liner out of this, like that would be how you would do it. All right. So yeah, increment T right there, and then place the new value X at ST subscript T, like that right there. So this is using the sort of newly incremented T there, like that. And again, notice that this is all just straight up O of 1, no loops, no need to like shift things around or anything like that. So it's all very sort of straightforward. Right? And then pop is basically just going backwards, right? If we increment T to push, we're just going to decrement T to pop here. So we can't pop if it's empty, so check to see if it's empty and do a stack underflow. Otherwise, we decrement T. And now the value that we just popped off is at the old T plus 1. So we return whatever is at index T plus 1 in the array there, like that. Yeah, again, like sort of straightforward, just all sort of nice O of 1. If you wanted to, you could do like the sort of vector trick and double the capacity when we become full there, like that. That would make your push run in O1 amortized time, but would allow you to basically like, push sort of forever like that. Another thing you could do is you could have T not be the index of the current top of the stack, but be like one above the top of the stack, like the next available spot. And that just like a plus or minus one to sort of like the various things that we're doing there like that. And of course you could make the change so that like pop returns a void, and then we would definitely need like the top or peak functions to sort of exist in order to make that work there like that. So just a few sort of changes that you could make to this. So you can build a stack on top of a linked list or on top of an array here. Now, what can you use a stack for? Well, like I kind of mentioned that like you can use it as like a to-do list kind of thing, where it's like you add new tasks via push, and then the top of the stack represents like what you're working on right now, the sort of current task. And when you finish a task, you pop it off there like that. When we add a new element, it's like right next to, it's like adjacent to the sort of old top, right? It's just right above it there. So that you can kind of think of it as that makes it easy for like the tasks to communicate. So like if a task that we're working on spawns a subtask, right? We push a new thing onto it there. We can send it information because it's like sort of right next to us in the stack. And also when a task finishes and gets popped off, it can like return information to the task that spawned it, because that's just right below it on the stack there like that. So because of that, if we use stacks as like a to-do list here, they work for things like tasks with subtasks, where it's like we're working on something and we discover while we're working on it that we need to like do some other thing in order to finish the sort of current task there like that. So we can't finish a task until all of its subtasks are complete there like that. You can think of it as like, the subtasks are like the prerequisites for this sort of main task, right? You can't finish your degree until you sort of take everything that you need to graduate there like that. And like, again, that might not seem like that. It might seem like a kind of specialized kind of things, but lots of algorithms actually fit into that kind of sort of pattern, even if things that like aren't obviously sort of like, tasks with subtasks. So for example, like function calls and returns use a stack to keep track of what the current function is, and also what is the chain of functions that were called to sort of get us there. We'll see a really fully fleshed out example of that when we do when we talk about recursion in module 3. But function calls and returns use a stack to keep track of sort of where we're at, like that right there. I'll show you an example of a little bit of checking the syntax in a string. Like you want to check to see if like the parentheses are nested correctly inside of a string or something like that. So you can do that with a stack there like that. And then finally, we'll see an example of evaluating mathematical expressions. So like if you have a string that has some math in it, we can use a stack to evaluate that and sort of figure out what its value is there. Although we do have to make a change to the sort of syntax of the math that we will accept there. So function calls and returns are managed by a stack of these things that are called like function call frames or function call records. So a frame maintains all of the information we need about a running function, like what are its local variables, what are its parameters, what line, like what part of the function are we currently executing. So the top of the stack is always whatever function is just currently running right now, what function has control of the CPU there like that. When we call a function, we just push a new frame onto the stack. We send it whatever arguments we want it to have as new parameters like that. And then because it becomes the new top, it immediately becomes the currently running function. When a function returns, we pop its frame off the stack there. And because it pops off, the thing below it immediately becomes the currently running function. But that was the function that called it, right? Like the function that called it is always immediately below it. So that just resumes the old function at the point where it left off. Like it picks up right where it left off without sort of knowing that like anything sort of weird has happened there like that. Again, we'll see a fully fleshed out example of how this works when we talk about a recursion there. Or I guess we'll see it right now. I guess I should have looked at this presentation before I talked about it. So let's say that we have this program here, right? We've got a main that calls a function f, and then f calls a function g, and then g doesn't do anything. It just returns here. So our program starts with main, right? So main is currently the top of the stack. When main calls F, we push a new record onto the stack, keeping track of the information about what is X. So X inside of F is 2 there. So now F is the current top of the stack. So like now F is running, right? We get there like that, right? Then we get to the point where F calls G. We push a new record for G onto the stack, keeping track of what is Y. So now G is running. When G returns, we're going to pop G's record off the stack, and that immediately resumes us at the point where we left off inside of F, and we still have that information about what X is in here. So F just picks up immediately where it left off. F runs until it hits the bottom of its code, and it returns, right? And we pick up back in main. So then we resume main right where we left off there like that. So like on the way down, right, during the function calls, we're sort of like adding things onto the stack. And then when things are returning, we're popping things on the stack to sort of get our way back out to main there like that. When main is done, right, when we hit the bottom of main, of course, we pop main off and the stack is empty, and that's where our program ends. Like basically, your program is done when its function call stack is completely empty, and whatever main returns becomes the exit code of your program. Another thing that we can use a stack for is checking like a string to see if it matches a particular sort of syntax here. So let's say that we have a string containing characters from this list here. So like various kinds of parentheses and then brackets there like that. So we've got a string and it contains like parentheses, square brackets, angle brackets, curly braces, and stuff like that. We want to determine whether the brackets are correctly nested within each other. So like in an empty string, there are no brackets, so those are correctly nested, right? Here, there's no the brackets are not inside each other, so those are correctly nested. But like here, right, the square brackets are inside of the parentheses. We want to make sure that those are correctly nested. And then this one down here is like obviously an extreme example, but everything is sort of nicely nested within other kinds of things there. Unless I screwed up somewhere and made a mistake. No, I think that's all good there like that. Incorrectly nested things, right? Obviously, you can't just have like a single, open bracket or a single closed bracket like that right here. Over here, we're missing, right, a closing square bracket. There should be a square bracket there instead of that sort of closing angle bracket like that right here. Again, here, we're missing that closing square bracket. It should be there at the end here. This one here is the interesting one. We have the right number of open and closes of different kinds of things, but they're not correctly nested. So like this last example shows us that we can't just count, okay, how many, open square brackets are there? How many closing square brackets are there? How many open parentheses are there? How many closing parentheses are there? And check the counts. This one correctly has one open square bracket, one closing square bracket, one open parentheses, one closing parentheses, but it's still wrong. They're still like not correctly nested within each other. So the algorithm to sort of check to see if the string has like the brackets correctly nested is we're just going to loop through the string one character at a time from beginning to end there. If we see an open bracket symbol, so anything from like this list right here, any of the open bracket symbols here, we're going to create a subtask to check if everything inside it is okay. Right? So we're like, all right, I need to check all the stuff inside of this here like that. So what that means is we're going to push the open bracket symbol that we see onto the stack to basically say like, I need to see if this thing is okay. That's my subtask. When we see a closing bracket, anything from this list here, right? So first we check to make sure the stack isn't empty, because we're going to be looking at what's on top of the stack. If the stack is empty, then there is no top there. If the stack is empty, then we have an error. That means there are too many closing brackets, right? If we had like, like a closing bracket, but there's nothing on the stack, that means all of the other things were sort of closed previously, and we have too many closing shapes there like that. If the stack is not empty, then we check the top of the stack to see if it makes sure that matches the current task here. If the top of the stack matches the closing bracket. So the top of the stack is going to be an opening bracket, right? We're looking at a closing bracket. So if the top and the sort of the start of the stack matches the current character, they're like a pair of, open close parentheses, open close square brackets like that, then we pop it off the stack. That means we've finished that task successfully. We sort of like found what we were looking for. If they don't match, that's an error. That means that like we had like a mismatch of there, like you tried to have an open parentheses and then close it with a square bracket or something like that. And then if we get all the way to the end of the string, right, we don't hit this error or this error like halfway through there like that. If we get all the way to the end of the string, the stack should be empty at that point there. If the stack is not empty, that means we had too many open brackets, right? We had like an open parentheses that was never closed, so it is still on the stack. It still got pushed onto the stack somewhere in the past, and then there was no closing bracket that sort of matched it to pop it off there. So at the end of the thing, we basically just say if the stack is empty, return true, otherwise return false there like that. So this is just a straightforward loop through the string here, right? An on time sort of task there that'll tell us whether those parentheses are correctly nested. If we use the C++ standard library stack, it sort of works like this. So I'm just assuming that we have these like utility functions that tell us, is a character an open parentheses, is it a closing bracket, and then this function here tells us for a pair of characters, like do they match, right? Is like one of them an open parentheses and the other one a closing parentheses. Like these are just like if-else things. I just didn't want to write them to make the slide longer than it needs to be here. So we've got a stack of characters, and then we're going to just loop over the characters in our stack here. And then the body of this loop is just a giant if-else here. Like there's no curly brace here because it's just one big if-else here. So if it's an open character, we just push it onto the stack there. If it's a closing character, then we do all those sort of checks here. So if the stack is empty, that means we had too many closing characters and we return false. Otherwise, if the stack is not empty, we check for a match. If they match, that's cool. Then, oops, here's a mistake. This should be a pop, not a top, right? Pop removes, top does not there like that, right? Otherwise, if they don't match, then we have a mismatched pair of brackets and we return false. And then if we get to the end of the string, down here, this is the end of the string at this point right here. If the stack is not empty, we return false because that means we have too many opening brackets. Otherwise, everything matched up and we return true. Another thing we can use a stack for, which is actually kind of related to the previous thing here, although it won't be obvious sort of how, is to evaluate a sort of modified form of mathematical expressions here. So like, normal math, you would write it as something like this, like 1 + 2 × 3 here. But the algorithm, like if you imagine having that in a string and you want to like sort of write a function that takes a string and returns an int, that's pretty gnarly because that like algorithm needs to know about like PEMDAS, it needs to know about parentheses and stuff like that. So instead, we will modify our mathematical syntax into something that is called postfix notation. So in postfix notation, we write the operators not like between the operands, like the plus is between the 1 and the 2, and the times is between the 2 and the 3. This is called infix notation, the way that we're sort of normally used to it. Right? In postfix notation, we write the operators after them. So 1 + 2 × 3 in postfix notation is written as 1, 2 + 3 times. So the plus operates on the things that come before it, and then the 3 operates on the things that come before it there like that. So what's the algorithm for evaluating this? What's the algorithm for sort of like, running these things and figuring out these values? Well, it turns out it only has like 2 rules. So we're going to loop over the input, symbol by symbol, like sort of, word by word, bit by bit there like that right there. And the 2 rules are just if the next symbol looks like a number, we push it onto our stack. If the next symbol looks like an operation, like plus, minus, times, divide, then we're going to pop 2 things off the stack, do the operation, and then push the result. And then when we reach the end of the input, whatever's on top of the stack is the result of the expression. Like that's just the answer to what we're doing there, like that. So assuming that we've already like split our input up into a vector of strings here, that has like this implementation here. So we have a stack of ints. Again, this is using like the standard library stack here. So this is hashtag include stack. Right, that's where we're getting this from here. So we're just going to loop over all the strings in the vector. This is checking to see if it looks like a number. So we're just checking to see if the first character in the string is a numeric character. If it is, we convert it to an integer. So that's what s2i does, is it takes a string, right, and converts it into an int. But it will only work with strings that actually look like ints. So like we need to verify before we do that our string actually starts with a number there, like that. Otherwise, if it looks like an operation, like a plus or a minus or a times or a divide, we're going to pop two things off the stack. So again, for the standard library stack, right, looking at what's on top of the stack and popping it off are two separate things. So I have to grab the top, pop it off, grab the top, and then pop it off like that. And then we just go through the operations and say, okay, if the operation is a plus, we're going to push a plus b. If the operation is a minus, we're going to push a minus b all the way down for all of them there. And then when we reach the end, whatever's on top of the stack, that is the result of our thing there. And if you want to like add new operators, right, that's just adding new stuff to the looks like an operation part of it there, like that. We'll see later. You can add variables. You can have things like x plus y, only that would be written as x, y plus. That's pretty easy. And then you can even add things like control structures, like if-else's and loops. And then you're moving from less of like a calculator and more towards something that's like an actual real programming language. So there are a number of these sort of stack-based programming languages. The most well-known one is probably called Forth. So if you want, you can look that up and see something that's based around sort of stack manipulation as its sort of key thing that it does there, like that. All right, so that is it for stacks there, like that. So if you want, you can move on to the video about queues, which are kind of like sort of mathematically the opposite of stacks.